Good morning or good afternoon, depends on where you are, everyone. Thank you for the Mutasser for the introduction. Today, I'm going to talk about rapid repair of hollow core columns. I would like to thank my co-author, a bunch of graduate students that work on this project, Omar Abdul Karim, Mohamed, Ahmed, and Sajat. Whole core columns is not something new. This is the I-5 Ravenna Bridge in near Seattle area. And the bridge was built in 1950s, and the columns for this bridge have a hollow core columns. So if you see over here, it is a 5-inch concrete wall, 5-inch thick concrete wall. And then we have a combinations of pre-stressed and the rebar as a reinforcement in single layer reinforcement. And then we have spirals going through the column. When we did the analysis, the moment curvature analysis for the cross section, it became obvious that the cross section is very brittle. And the reason for this here is a finite element analysis for the columns. You would see very quickly we reach to an ultimate strain for the unconfined concrete from the outside over here. Recall that the spiral are at the middle. This is the reinforcement over here. If you see the very tiny small yellow dots over there, these are the reinforcements. So very easy we reach to unconfined ultimate strain for the concrete, the red area over there, and then you quickly lose those which represent more than 50%, of the area under compression. So this has led to rapid degradation on strength and hence relatively low ductility for the columns. There has been some research at University of California, San Diego, where they moved the reinforcement from the middle of the concrete wall to the outer side, which improved the ductility. However, the ductility is still displacement ductility. They reached the displacement ductility of roughly 3.5, which is not adequate for high seismic regions. So this is why the hollow core columns are not very popular. It's not something new, but it's not very popular because of the lack of ductility. So another research team from Korea proposed some measures to improve the ductility, and they were successful. They reached very high displacement ductility. However, as you see here in the picture, they rely on tying, first of all, they provided 2 layers of coaxial reinforcement, and then they tied every single bar. So if you think from a structural perspective, that the performance was more than excellent. However, from a construction perspective, that's a very complex construction and did not survive the construction market. So what we did over the last few years over here is to use a hollow core column that consists of an inner steel pipe and then concrete shell and then FRP tube. So what are the advantage of this hybrid system? First of all, was cutting the concrete from the middle over here. So for example, if we are talking about like a typical bridge column diameter here in Midwest, it's probably 5-6 feet diameter. So about 2-meter diameter columns. We're talking about concrete wall thickness over here of less than 5 inch, so probably 4 to 5 inches. So that's about 10 centimeter or 100 millimeter concrete wall thickness. So we significantly reduce the weight, so about 75% less concrete material. You can link this also to the you're using less material, it's more sustainable, and so on. We have two pipes, the inner steel pipe, the outer FRP tube, that they can act as a stay-in-place formwork, so we don't have formwork that can significantly cut on the construction time. We have an excellent confinement concrete. Concrete cannot escape, cannot go anywhere, because from inside you have the steel pipe, from outside you have FRP tube. So it's as if you use a spiral, but with the pitch of 0. It's a continuous. So we have an excellent confinement. We move the steel pipe to inside the column, so it's protected under different barriers. You have the FRP outside, you have a relatively thick concrete wall outside, that's FRP 4-inch, 5-inch of concrete, and then your steel pipe. So it's well protected from outside environment. So that are the advantages. So we took that idea to the lab, and we did construct our columns over here. The columns is almost half scale columns. The height of those columns is 2.5 meters, roughly 2.5 meters, and the diameter is 0.6 millimeter, 0.6 meter, with an aspect ratio of approximately 4. This is the one to the left over here is the reference column. So for the reference column, this is a solid, has a solid cross section, and about 1.2% flexural reinforcement. That's 8 number 7, and also we used spiral. So the spiral is number 4 at every 3-inch, going through the column. So this is a very typical bridge column in Midwest, with one exception. They typically don't use a spiral here. They typically use hoops rather than a spiral. But we try to improve the seismic performance of the solid column, since we're going to compare it to another. Our system is very well confined, so we decided to move to use spiral. The hollow core columns, as I mentioned, consist of the inner steel pipe and then the FRP pipe outside. The steel pipe, this is something also relatively new here. So what we did was for the construction, we proposed 2 different construction systems for MoDOT, Missouri Department of Transportation. The first one is a stay in place, precast or cast in place. So for the this is the FRP tube, very lightweight. This is my former student, Omar Abdel Karim, carrying the pipe. This is my student to the left, Sajid, try to fix the strain gauges inside the steel pipe. Every pipe has about 70 strain gauges mounted to measure the horizontal, or the circumferential and vertical or axial strains on the pipe. So from a construction perspective, this is one option for the construction. We have the formwork for the footing. We have the rebar for the footing. We inserted the inner steel pipe with enough development length. And then next step is to have the FRP tube and then fill in between the 2 tubes with concrete. The FRP tube was not embedded on the footing. So only steel pipe is embedded on the footing, and then the FRP is terminated, truncated at the face of the footing. So any moment transfer occur, like, on the tensile, all tensile stresses occurred on the steel pipe only. And this is not a single column. This is not a single footing. So those are 2 columns. There is a hairline over here. The 2 footing are just next to each other. So we have the one to the left. This is the column with the solid cross section. The one to the right is the hollow core columns. Here is our test setup at Missouri SNT. So this is the reinforced concrete column. This is the footing, and this is just pedestal to give us the required height to match the height of the jack. So this is 2 actuators, and then this is the external pre-stressing representing the axial load, and then we apply the load back and forth to mimic an earthquake. So here is the first set. We did, like, as I mentioned, we did, like, different students work on this project and different testing sets. So this is the first set that we tested. So on this set, we had 5 columns. The first one here is the reinforced concrete, and then this is our reference, and then we have 4 different options with different parameters for the hollow core columns. So the first thing or the first parameter that we changed was the thickness of the FRP. So FRP is really probably one of the most expensive element. The FRP tube was one of the most expensive constituent on this column. So we looked at, we tried to optimize the thickness. So over here we used the common one was 3/8 of any inch thick tubes, while on one of the columns we went to 1/8 of any inch thick tube. The other parameter that we looked at is the thickness of the steel tube. So again, the common is 1/4 inch, but also we tested one with 1/2 inch. Concrete wall thickness, common is 4 inch, and one was tested with 5 inch. One of the parameters also when you are talking about like the cost of the FRP tubes, the common reason over here for the tube itself was epoxy, but for one of the columns we use isopolyester in order to try to reduce the cost. Isopolyester is much cheaper than the epoxy resin. And this is the test. So as you see, we're going back and forth. So you see the opening here at the bottom of the, you see the opening at the bottom of the column. This is the load. This is the load that was applied. And now, after we tested the first set of columns, MoDOT was Missouri Department of Transportation was curious about how we can repair this after an earthquake. So what we proposed for them is a rapid repair technique that consists of first we clean the column. So I'm not sure if it's clear over here, but this is a column, a hollow core columns that was tested first on the first phase. And then after that, it has some rupture on the FRP tube, and went back and cleaned the columns, removed any big chunk of concrete that was loose after the test. And then we applied the 3 layers of glass fiber. So we applied 3 layers of glass fiber, and then those took about 1 hour for applying the fiber. And then, we don't want to wait the full time for curing the fiber, the glass fiber. So what we did over here, we created what we called a heat chamber. So using the sonotube, so we have the sonotube, and we isolated the sonotube from the outside to ensure that it's thermally insulated. And then we have opening on the sonotube where we apply heat. Used 3 heat guns and applied high temperature of 50 Celsius, not directly to the FRP, but within the chamber. So the chamber had a constant. We have a lot of thermocouplers to measure to ensure that the temperature was constant at 50 degree. So with those thermocouplers, we let the 50 Celsius for about 4 hours. And then after the 4 hours, this was the selected curing time for the FRP. And then after that, after the 4 hours of thermal curing, we did epoxy injection. So this is the FRP repair material. And here we have the hoses for epoxy injection. And the epoxy was injected from the bottom of the column, and the epoxy was injected from the bottom of the column, and we have hoses on the top of the repair to ensure that the different hoses to ensure that the grout was floating very well from the bottom to the top. The grout injection took about 1 hour. So in total, the total repair time was about 6 hours. 6 hours, one time for 1 hour for the wrapping the glass fiber, 4 hours heat curing, and then 1 hour for the grout injection. And then after the 6 hours, the column was very much ready for testing. However, the instrumentation, because we removed all the instrumentation before the repair, so it took also another few hours before testing the columns due to preparing the column for testing. But the repair itself took about 6 hours. And then this is the column after the repair. Here are the 5 columns that we tested on the first one, including the repaired one. So we had different modes of failure. So to the left over here, we have a very typical plastic hinge on the reinforced concrete column. This column was well designed, so nothing really surprise over here. We have a very typical plastic hinge with rebar buckling and some rebar rupture. This is a spiral with some damage to the spiral as well. To the right over here, the 2 columns, the yellowish one with the epoxy resin FRP, the one to the far right, greenish one, is the isopolyester resin with a very thin FRP, the 1/8 of an inch FRP. And as you see in both of those, we have rupture on the FRP. I forgot to mention that the fiber on those pipes were plus or minus at the winding angle for the fiber was plus or minus 53 degree. This is why we have, if you see over here, all the fiber at kind of a diagonal angle. This is one of the column where we did not have enough development length on the for the steel pipe, so we had a pull out failure, and failure occurred mainly on the footing, not on the column. This is also some steel rupture on one of the columns. This is the column to the left over there. This is the original column. This is the column to the this is the column, the original column, and this is the same column after repair. So like on the first one, we ruptured the FRP, but on the second one, there was no rupture in the FRP itself. And we inserted some cameras inside the columns to watch the performance of the steel pipe. So this is the inside the column. So if you see over here, this is the elastic buckling of the pipe. So you see this is the side of the column. So this is the very bottom of the column. So this is the very bottom, this is the side. And here we see the buckling, elastic buckling of the side of the steel pipe. And then once you start to remove the load, this was cyclic load. So once the load was reversed, the pipe went back to the vertical position. Here is a comparison between the hysteretic response of the 2 columns. The one in blue is the original column. The one in red is the retrofitted one. So the vertical axis here is the moment in kilonewton meter. The horizontal one is the drift. So as you see here, the repair was not able to achieve the full capacity on one side. The difference was probably about 10%, but on the other side, we reached the full capacity of the column, the original column. What's more important is really, if you look for the red loops over here, the repaired one, we achieved very much better energy dissipation and higher displacement. One of the shortcomings of the repair was the initial stiffness. So the initial stiffness, if you look here for the blue one, is much higher in terms of initial stiffness compared to the red one. This was mainly due to the micro cracks that occurred in the on the concrete, and potentially any slip that happened on the steel during the first phase of testing before the repair. Here is the 5 columns, the 5 original columns, the hysteretic loops of those columns. So the one to the far left over there, this is the conventional concrete column. Again, no surprise, it's a very nice fat loops.
Sorry to interrupt, Dr. ElGawady, you have 3 minutes.
Okay. This is very much similar to reinforced concrete. I mean, if you see this one, you probably cannot tell if this is a reinforced concrete or if it's the hollow core column. So it behaves very much similar to reinforced concrete. Very nice plateau. The others has different modes of failure. Here, the one with the FRP early rupture. To the bottom over there, this is the pull out, and you see the slip that occurred, the benching that occurred in the hysteretic loops. This is also a well-designed column. So here are the envelope of the envelopes of the columns. What's important for us here is the repaired one. So the green one over here is the repaired column. The bluish one over there is the one before repair, the original one. And as I mentioned, we're not able to 100% recover the strengths. However, we displayed better displacement and energy dissipation. This is the reinforced concrete column. We reach very much similar strengths to reinforced concrete column and also same level of ductility. And I'm going to skip the. So this is just a discussion of the system from a deformation perspective. We have the concrete dilate, and when the concrete dilate is expand, there was an expansion against the inner steel pipe and outer FRP pipe. There is interaction between the there was an interaction between the system. So if whenever we have the steel pipe, whenever we have this are two cross section, the same steel cross section. However, to the left we used a thinner FRP pipe, and then to the right a thicker steel pipe. So whenever we have the dilation, the concrete dilate toward the weakest section, whether it's the FRP or the steel. So to the right over here, we see most of the dilation occur toward the FRP. On the other side, you see here it's only 2,000 microstrain versus here 3,000 microstrain. And then we also looked at the vertical dilation. This is along the height. Those are just the strains. And then we propose an expression for the embedment length. How long you would like to embed the FRP, the steel pipe inside your footing to reach to develop your full capacity of the columns. That I reached to the end and conclusions of my talk over here. We have hollow core columns behaved better or equivalent to reinforced concrete columns, well-designed reinforced concrete columns. However, we have a lot of advantage of the developed columns over there. We have also developed a practical repair system that talk about 6 hours for the application. The hollow core columns developed a high energy dissipation comparable to those of the reinforced concrete columns, which was one of the major issue for existing hollow core reinforced concrete columns. Thank you so much for your time and attention. Ready for questions.
So thank you, Dr. ElGawady. Okay, so there is no question. I have one quick question, Professor. Since both steel and FRP tubes are plain, did you see any relative slip between the concrete and those two tubes during your test?
Yeah, we did measure some slip that was more or less like elastic slip. So it occurred whenever those are under tension, and then once it's reversed, they close the gaps and they act together again. However, the slip relatively was not that high. So the slip mainly occur between the concrete and the steel rather than between the steel and the footing. So the slip between the steel itself and the footing was minimal. However, the majority of the slip coming from the sliding of the concrete wall shell over the steel pipe.
Okay, thank you. Thank you, Dr. ElGawady, for your nice presentations.